Here are your Chapter 3 notes for AP Physics. Introduction to Vectors. A scalar has magnitude but not direction. Examples of scalars include time, length, and mass. A vector is a quantity with magnitude and direction. Examples of vectors include velocity, for example, 55 miles per hour to the east, and force, 10 newtons up. Notice that both of these quantities have direction. Scalars may be added and subtracted with ordinary arithmetic. For example, if we take time, 5 seconds plus 6 seconds equals 11 seconds. Vectors must be added graphically because direction must be taken into account. For example, 5 kilometers to the east plus 6 kilometers to the west does not equal 11 kilometers. It equals 1 kilometer to the west. Let's take a look at what this might look like. First of all, the directions north, south, east, and west need to be established. So we've got north is up, south is down, east is to the right, west is to the left. Here I've got 5 kilometers to the east represented by an arrow. The length of the arrow tells me how many kilometers, and the direction tells me it's to the east. My west arrow is a little bit longer because we're talking about 6 kilometers instead of 5, and its direction is to the left, which represents to the west. In order to find out my resultant, I start at the tail of my first vector and go to the head of my second vector. And it turns out that the result of 5 kilometers east and 6 kilometers west is 1 kilometer, and my direction is to the west. If I take my 1 kilometer vector, and put it on the coordinate plane, I can see that its direction and its length remain constant even when I move it around. Let's look at another problem. Add 5 kilometers east and 6 kilometers north. In order to solve this, first we're going to sketch the vectors. So here I've sketched the vectors, 5 kilometers to the east and 6 kilometers north, and I've added them head to tail. This is one way to do this, and this is actually the sum 5 kilometers east plus 6 kilometers west. I can also add them in the opposite order. I can add 6 kilometers north plus 5 kilometers west. This is similar to saying that 6 plus 5 is equal to 5 plus 6. Now I'm going to draw the resultant vector. The resultant should be drawn from the tail of the first vector. Here's the tail of my first vector, to the head of my second vector. So I'll go ahead and draw that in. Just going to draw a straight line as best I can. Notice that the resultant vector has the same magnitude and direction regardless what order the original vectors were added. So even if I draw 6 kilometers first and 5 kilometers second, my resultant vector should be the same. In other words, I should be able to pick up my resultant vector, and it should be the same regardless of the order in which I added the original vectors. Now it says determine the magnitude of the resultant vector using the Pythagorean theorem. Okay, well, I'm quite familiar with the Pythagorean theorem, so I'm going to take 5 squared plus 6 squared equals r squared. R squared. So I'm going to call this vector, my red vector, my resultant vector. So when I add these, I have 25 plus 36 equals r squared. 25 and 36 is 61, so 61 equals r squared. So r equals the square root of 61, and then my unit on this would be kilometers. So there's the length of my vector. Now, the last thing that I need to do is get the angle of my vector. Now the angle of the vector is measured on the coordinate plane. So I want to think about what a coordinate plane would look like. And I will draw one here. Okay, so what if I were to take a coordinate plane and place it at the tail of my vector? There's my coordinate plane. I've got my 4 quadrants. Recall also with the coordinate plane that we've got angles. So we start at 0 degrees and we go counterclockwise to measure an angle. I can see in my other drawing, this might be easier to use, that in order to get this angle, theta, I could use inverse tangent. 6 kilometers is my opposite side, and 5 kilometers is my adjacent side. So I could say that the tangent of my unknown angle is equal to 6 over 5. Then I would get out my calculator. Make sure your calculator is in degree mode. I'm going to type in inverse tangent of 6 divided by 5, and I get that I'm not in degree mode. Let's try that again. Okay, we get 50.2 degrees. So when I solve this, I get that theta is equal to 50.2 degrees. So now my answer has the length of the vector and also the direction of the vector as measured on the coordinate plane. Let's look at another skill. Let's look at the skill of resolving vectors into components. The problem says, find the component velocities of a helicopter traveling at 95 kilometers per hour at an angle of 35 degrees to the horizontal down. Step 1, sketch the vector on the unit circle. Okay, again, what I would like to do, or I would like you to do, is I would like you to imagine a coordinate plane. So here's my coordinate plane with the angles measured. 95 kilometers per hour at an angle of 35 degrees to the horizontal. So now what I'm going to do is I'm going to draw my vector. So 10, 20, 30, here's 35. Try to put this right at 35 degrees. So there's my vector. I've sketched it. Then it says use the formulas to find v sub x and v sub y. Okay, so the length of my vector, 95, that is r. Oops. So r is 95. And 35 degrees to the horizontal down. Now this 35 degrees, on the unit circle, you could call it negative 35 degrees, or if you measure all the way around this way, you would be measuring 325 degrees. Now I'm going to plug those values in to find the components. So for Vx equals r cosine theta. For my values, I would have 95 times the cosine of 325. Eek. And for Vy, I would have r sine theta, or 95 times the sine of 325. Oh, sorry about my handwriting there. Okay, now I get out my trusty calculator, make sure it's in degree mode, type in those values, 95 cosine 325. 95 sine 325. For my horizontal value, I get 77.8. And that was kilometers per hour. So we maintain the same units. In the vertical, I get negative 54.5. And the same units, kilometers per hour. Okay, so let's think about what that means for a moment. The horizontal component of my velocity, let me pick up a different color here. Horizontal component of, we'll get rid of this. Horizontal component of my velocity is how far over I would have to go to get to the end of this vector. And that distance is 77.8. And this vertical component, negative 54.5, is how far down I would have to go to get to the end of this vector. And of course, R was 95. So basically what I have here is a right triangle, and I've just used SOHCAHTOA to find the two sides of the right triangle.